And hello, welcome to this edition of Radiation Heat Transfer Learning Journal. Welcome everybody. It is time for the radiation transport equation, otherwise known as the RTE. Alright, so what is this about? Well, this is probably one of the most scary things in radiation. Cue dramatic music. Dun dun dun. Okay, so enough with the jokes. So what are we dealing with here? So let's say you have two surfaces, or an arbitrary number of surfaces, any number of surfaces. Alright, normally what we have briefly touched on is the heat transfer between these two surfaces, right? So let's say this one was at T1 and this one was at T2, or any other temperature distribution or heat flux kind of a distribution. What is the radiation transfer between these two based on their shape, based on emissivity, etc. We only covered gray diffuse surfaces because that's about all we can do analytically. Right? Any more than that probably requires a computer of some sort. Now, the equation was pretty simple in theory. Well, even though those formulas can get a little complicated once you have lots of surfaces, but we assumed everything in between was a vacuum. Now what happens if the stuff in between is not a vacuum? Not a vacuum. Alright, not a vacuum. Then what are you gonna do? You're gonna have a little bit of trouble here. So this is what we call participating media. Because the media, spell it correctly, participating media or participating medium. Alright, I'm gonna cut this all. I'm gonna paste it here. So if the stuff in the middle is not like it's a participating medium, it is something. It could be a gas, it could be a liquid, it could even be glass. So I just give you some examples. Gas, it can be a liquid, it can even be a transparent solid, like e.g. like glass. And it does allow some form of radiation to go through the medium itself. However, sometimes when radiation passes through, it gets absorbed, or sometimes it gets reflected partially as it goes through the medium, and all sorts of funny things happen. So that kind of messes up our equations a lot. So how do we deal with this this kind of thing? So how do we deal with participating mediums? Okay, so this is where we start looking at radiation transport equation. So this is the radiative transfer equation, or radiative transport equation. This is based on chapter 10 of Michael F. Modest. It is here. Okay, so I have also, I'm going to start trying to go through step by step what goes on in this participating medium. So let's clear the paint here, and we can start with maybe I'd like to do a black, and maybe yeah, this is good. It's almost like Khan Academy. Oh well, a black surface, a blackboard with yellow. Hi. Okay. So let's say you have radiation going through said medium. Okay. So next time I want to do paint, I'm probably going to do things like that. Okay. So you have radiation. Using my mouse to write. All right. So we go through some sort of participating medium, right? What can happen? What can happen? Okay. So I think what can happen? Yeah, that's at least more legible. So put a question mark there. Okay, first thing first, that's what we discussed in the glass example. Sometimes radiation can be absorbed. Okay, radiation can be absorbed. Alright, absorbed. What else? Okay, what else? So what's absorption mean? Absorption means that when it goes through, the radiation is actually captured by the molecule or atom, and it becomes heat, right? It becomes heat. So the photon is absorbed, the radiation photon is absorbed, and becomes heat. Okay, so the photon is absorbed and becomes heat. That's one of the things that can happen. Second thing that can happen, the radiation trajectory can change. So it bounces, the photon actually bounces off a molecule. So we have a photon here. It looks at this atom and then, oh, pong! Yeah, it gets scattered off into a different direction. So this is called scattering. Okay. So scattering is basically the radiation changes direction. So similar to how sunlight enters the atmosphere and goes through a water droplet perhaps, and then it kind of gets refracted. I mean, that's one of the things that happen, but that's what happens when sunlight gets scattered into a rainbow, or white light gets scattered into its various different colors. That's one of the examples, of course, but that happens between the boundaries. Sometimes light can also be diffusely scattered, so or reflected, or so this is basically, there is reflection happening on the micro scale, and then it's just changing its direction all over the place. Okay, so what else? We know that if the medium is very hot, let's say 1200 Kelvin for example, the medium actually starts to emit its own radiation, right? So emission is possible. So if the medium is so hot, we can actually have emission happening. So that will actually, make the radiation stronger. So let's say you have a 5000 Kelvin body. You have a little bit of radiation coming in from the left, but by the time it exits on the right, the radiation will be much stronger. If you have a small bit of ray here, a small ray, the small ray on the left, it goes through this 5000 Kelvin kind of a what do you call that? Kind of a medium. It will get augmented. That's the word we use, augmented. Okay, augmented, and you have a strong radiation coming out. Why? Because this medium is so hot, it is emitting lots of radiation. Okay. Alright. So these are among the three things that can happen. So let's take a look at the textbook. Alright, so the textbook uses this term called attenuation. Attenuation means that the radiation beam can get weaker. Right, so the radiation beam gets weaker due to this absorption and scattering. So absorption and scattering, we have briefly discussed it. And then we can have augmentation by emission and scattering. Now, we were talking about emission just now, this emission. right? That means the medium is so hot that it actually strengthens the radiation passing through it. And scattering, yes, it can also strengthen the radiation going through it. Why is that so? Now let's take a look. I'll use a green highlight. Let's say there is this radiation coming through here. All right, but let's say there's this is your direction I. This is your direction J. So, or it can be direction 1 or 2. So let's say the radiation from direction J just so happens to be scattered by an atom into the direction of I, right? So what is the radiation that's going in this direction? It will be twice as strong, or at least it will be the original. If this is just a scattering medium, it will be the original ray plus whatever is scattered in this direction I, right? So this is called scattering, in scattering. Okay, so it means that radiation from other directions is being scattered, okay, to make the radiation in this direction I stronger. So it doesn't just have to be this particular direction here. J can represent from this direction, etc, etc. So let me use a red. It can be from this direction, as long as it is scattered in this direction I. Okay, as long as it is scattered in this direction I, that radiation gets stronger. So scattering has two effects. So yes, it changes direction. So radiation can be scattered from direction I out, so that's out scattering, or it can be scattered from other directions back into this direction I, so that's called in scattering. Okay, so these are 4 effects we need to take account for. So what happens when radiation goes through a participating medium? So first we have what we call the attenuation. So this is the weakening effect. All right, attenuation. So we have outscattering. That means what I said earlier, the radiation can be scattered out into different directions. We can have absorption. So the radiation is being absorbed by the atom or molecule or whatever, and then it gets transformed into heat energy of that molecule. So that's the attenuation effect. Then what happens as well? You have a augmentation. So the strengthening effect. Okay, so you, like I said earlier, you have in-scattering, and then you also have emission. So in-scattering, it means to scatter from other directions, in direction J, for example, to I, and what do you call that? Emission is due to, well, if the body is so hot that it's emitting radiation in this direction, then you get stronger radiation coming out from the other side. So that is what emission is talking about. So these are the 4 things you kind of need to consider when you start thinking about the radiation transport equation. Okay, at least when you talk about it in theory, it doesn't seem complicated, but okay, the math of it is pretty challenging, especially because of the scattering terms, because now you need to take into account direction. So yeah, this is I guess part 1 of the radiation transport equation. Probably in the next video we'll start talking about each of these terms a little more in detail, at least start putting some math to it. Okay, so thanks for watching. I'll see you guys next time. Bye bye.